Thanks, Sven. Thanks, everyone. Yeah, today I would like to talk about a new paper about metamorphic burial rates and the evolution of plate tectonics. Yes, so let's start with what we know. This is a representation of the proposed onset for plate tectonics in the past 50 years, and although there's quite a scatter in publication dates, there's a general consensus for a transition period between stagnant lead and bobbing tectonics around 2.5 to 3 billion years. On the other side, we also have the abundance of low thermobaric ratio in the metamorphic record, which argue that modern subduction is not really up and running until 1 billion year. So what does this evolution actually reflect? Do you have one starting date, multiple starting date, or both? If you base the idea that the evolution of plate tectonic is linked to the cooling of the mantle, there is not much room for multiple starting dates. But this also fails to explain why we have periods in Earth history, such as the Boring Billion, where nothing really seems to happen, and why Archean subduction didn't trigger generalized plate tectonics. So let's consider for a minute that you are a new driver in a new car. You go in a car, you switch on the ignition, and the engine is on. That's the easy part. But to make the car move, you need the right amount of pressure on the acceleration and the clutch pedals. And you also need to remove the handbrake. Combined with your lack of experience, the likelihood for stalling, damaging, or shutting down the engine is quite high. Only time and experience will allow a more sustainable, efficient way of driving. Why am I going with that? In 2019, Sobolev and Brown suggested that erosion and weathering of crystal material lubricates subductions, hence enhancing recycling at peak moment of Earth history. Therefore, while plate tectonics engine driven by mantle convection could have been switched on as soon as the Hadean, it seems that the acceleration, brake, clutch, pedal are controlled by surface processes. In order to quantify this aspect, we revisited Earth metamorphic record or metamorphic signal by incorporating information on the prograde path. Why is it important? Well, classic compilations on metamorphic condition compile PT conditions and peak metamorphic ages to define absolute evolution of the apparent metamorphic gradients or thermobaric ratio through time. But this AMG only do not allow full comparison between Phanerozoic and Precambrian metamorphic conditions, especially for low thermobaric ratios. By considered timing of the deposition or formation of a protolith of the surface, we can determine in convergent settings the apparent burial rate for a given rock, which allow a direct relative comparison between samples of same apparent metamorphic gradient. Using Brown and Johnson's latest compilation as a reference point, we build a new metamorphic database integrating this new information. Due to the lack of information on the edge of deposition or formation of some rocks in a database, obviously our database is smaller than the apparent metamorphic database suggested before. Here we plot the log of apparent burial rates as a function of time. The color code is the associated apparent metamorphic gradient. We also reported the end onset for plate tectonic or the transition period. We then perform structural analysis on the metamorphic time series, both for the AMG and the ABR, to detect statistical relevant breaks in the time series. The analysis of the AMG in red reveal breaks at time of supercontinent in assembly phases and match partially the breaks that have been identified by Brown et al. In 2020 in gray. The identification of structural break in the apparent metamorphic gradients has been argued as evidence for the presence of bimodal metamorphic belt as soon as 2 billion years ago. Structural break in the apparent burial rates are less important in blue and only appear during supercontinental assembly from 1 billion years onwards. The most prevalent break, both in apparent burial rate and apparent metamorphic rate gradients, occurs around 500 to 550 million years following the breakup of Virginia and the early stage of assembly of Gondwana. Having access to both the thermodynamic ratio and Euler rates allows us to define n number based on distribution. So for data younger than 500 or 550 million years, where the most prevalent break is, we can see that they both define bimodal distributions. IMG have a dividing value of 500 degrees per GPA, and apparent Euler rates have a dividing value of 2.3 kilometers per billion year. The dividing value for IMG is more or less that have been calculated before in other studies. Additionally, kernel density estimates on the full dataset defined a mode at 0.7 kilometer per million year and 900 degrees per GPA, which we interpret as the metamorphic background noise which exists along for the entire duration of Earth history. This bimodal distribution allows us to create a 4-quadrant classification in which we can follow the distribution of the metamorphic data from the Paleoarchean. To have a better, this is what we obtained if we have this variation in time. To have a better understanding of what it means in terms of evolution, we divided the data set according to the main structural breaks in a metamorphic time series. And this is what we have. We report in red. The red dot is the background noise, and the dot with labeled M is the average modern or contemporaneous subduction conditions. This distribution in recent rock is less than 200 million years as a clear bimodal distribution with fast and cool subduction and slower and hotter bark-arc metamorphism or crystal thickening. In the rest of the Phanerozoic, we also have the presence or slower subduction or subductions, and the period between 500 and 3,000 million years display a very similar distribution, with most of the data concentrated in the left-hand side of the gradient. Finally, for the Paleoarchean, we also have terrains that plot within the top right-hand gradient, and these terrains, which are Pilbara, Barberton, and Isua, are classic in map of the Dome-Kiel geometry. So it seems that we have a completely different type of tectonic there. Therefore, we can define these 4 quadrants as follow. So we have the crystal thickening and bark-arc metamorphism in the top left-hand corner. And then what we call Archean tectonics, which will remain to be quantified later. And then at the bottom bits, we have slow subductions and fast subductions. Importantly, it has been argued, as I argued before, we have bimodal metamorphism since the Paleoproterozoic, but from the thermodynamic point of view, but the true bimodal metamorphism only with fast subduction only occurs in a Phanerozoic. There is also a significant resemblance between the 3 Precambrian stage between 550 and 3,000 million years, which could suggest that they might represent 3 different attempts at launching sustainable plate tectonic mechanism. To test this hypothesis, we look at how the metamorphic signal deviates from its background noise, which is basically just the Euclidean distance between the background noise and any point in the 4-quadrant system. So we reported here in this graph the Euclidean distance between the metamorphic ground signal and in the 4-quadrant space per being of 100 million years. And the red is for period where we have an increase in Euler rates, and the blue a decrease in Euler rates. We can see that there is both an increase in deviations from 3.2 billion years towards 1.2 billion years. And there is also, before we have a drop and then we start to increase again, and we have similar period 2 and 3. Then after that, period 4, we have a decrease in deviation from the metamorphic signal, which then is followed by a net increase that keeps going all the way to the quaternary repeating period 5 and 6. Therefore, there seems to be radical changes between period 3 and 5, which we argue might be due to like a major failed attempt at generalized plate tectonics at the end of the Paleoproterozoic. In order to compare more these 2 and 3, for instance, we can also look at the diversity index. So we took some tools from biology, and then we used the Gini-Simpson diversity index, which is given by this formula that we use in a 4-quadrant system again to evaluate diversity. High diversity is equal to 1, low diversity equal to 0, and you can try to compare the diversity in metamorphic signal for the different continental cycle. And what we can see is the diversity for period 3 almost reaches diversity which is equal to the diversity in metamorphic data signal at the beginning of the Phanerozoic. And we have also this major break at the end of the Paleoproterozoic when diversity is equal to 0 and starts to pick up again. So such behavior, we argue, is then compatible with the slab avalanche hypothesis and the feedback loop hypothesis on the maintained of plate tectonic efficiency through time. It is possible, and it has been argued before, that there might be several episodes of material avalanche, crystal material avalanche in the mantle, but the most prominent one would happen at the end of the Paleoproterozoic. And if you look at other aspects of geological records, you can see that this coincides with a peak in crystal signature in eruptional material in green. As you can see, we have like more lead in the eruptional material at the end of the Paleoproterozoic, and also coincide with a local low in the mantle protection temperature, the red dashed line for models that involve only episodic plate tectonics. At the surface, this is echoed by the orogenic belt, the percentage of active orogenic belts and the delivery of sediments into trenches and convergent settings in blue. It is then possible that we have surface conditions that are more or less timely aligned to mantle conditions at some point in our history. Therefore, we come with the following scenario, where we have a known set of mobility tectonics around 3.0 billion years, and this is followed by a failed attempt at generalized plate tectonics at in the Paleoproterozoic. However, we think that because the mantle might be probably still too warm to allow efficient convections, if we just put a significant amount of crystal material in the mantle, this will jam the plate tectonic engines, maybe by delivery or surplus of volatile elements, and we'll need the entire period of the boring billion to recover before we start having surface processes and mantle processes aligned and in tune, which allow sustainable plate tectonics at the dawn of the Proterozoic, of the Phanerozoic. Therefore, this change in diversity in a metamorphic signal evidence the sustainability of plate tectonics regime through time. And if we stretch a bit further, this evolution also echoes changes in the size of organisms, suggesting there might be a connection between geological and biological diversity. To conclude, our compilation provides new classification tool for tectonic settings. We obviously need more data, and there's also the issue of preservation bias. But we hope that this new data set will help to constrain better numerical modeling and crystal modeling. And finally, on the more philosophical touch, the evolution of Earth, it doesn't follow a linear path. It's just a record of attempts and failure that build on top of each other. And it is a pattern that echoes through different aspects of science, through time and space. Thank you.
Super, thank you, Gautier. Does anyone have any questions in the chat? So I guess I'll start with one then, Gautier. You had your sort of quadrants where you split up tectonics into sort of 4 quadrants, and you had sort of fast and slow on the bottom, and then you spectated in the top right the Archean tectonics. So what are you sort of spectating for the Archean tectonics?
Well, it's always the question that if we have this classic vertical tectonics happening, do we like have similar thermobaric gradients but different speed? So in our discussion, it's just like we argue for this type of vertical tectonics, but we have free data for the Archean. So again, we need more data for that, I think.
Yeah.
But the thing is, like, it seems to point towards that the things that we have subduction going on, but our data set, our new compilation seems to say otherwise.
So Richard's commented that it's great that you're doing some more statistical analyses of this data set. And Nick Roberts has got a question about what do you think was going on with the boring billion in your mind?
Well, that's a big question. So I think that remains to be quantified. I would just say that because we think that we have this huge avalanche of material down in the mantle, it must do something in terms of disturbing the entire system. What it does specifically, I think that's, yeah, that remains to be quantified, really.
Super. All right, we'll leave it there then. Thank you, Gautier.